Hi everyone, this is Dr. Hopkins with the next in a series of videos explaining Chemistry 472 Thermodynamics. And today what we're going to do is define work, at least work we're going to use. So before we define work, we need to realize that we're dealing with, at this point, the first law of thermodynamics, and we're going to talk about the first law of thermodynamics for quite a while here in this course. And as you remember, a law is a simple expression that explains a broad number of observations. It does not give any kind of theoretical basis. It's just this is what happens. Okay, so the first law of thermodynamics, simply stated, is energy is conserved. Okay, so that's one way to put it. The other way to put it, the other thing about laws is that we can usually come up with some simple mathematical expression, which is shown in the middle here, where we have the total internal energy change is equal to the change in heat plus the change in work. Okay, so we're going to define our energy in terms of whether it's heat or work. And so heat is typically thermal energy. Work, we're going to use a physical definition, which we're going to describe in a minute. Now, what I think is really interesting about the first law of thermodynamics, if you think about it, is that the energy of any isolated system, like a universe, is unchanged. That means that at the Big Bang, at the beginning of the Big Bang, we had X amount of energy, and now we still have the exact same amount of energy because the first law of thermodynamics tells us we do. All right, let's go to work. So work in the physics definition is movement of matter against a force, or basically in a force field. You can think of if you have to move versus gravity, you have to do work. Gravity is not particularly relevant force field for chemistry, so if you have to move something in an electrical field or maybe surface tension, or in our case, what we're going to focus on are pressure volume, so moving versus a pressure. It's molecularly interpreted as concerted motion of the molecules and atoms, so it's occurring at a particular boundary potentially, and then work is also a path function, so it depends on how you do it. So how much work you have to do depends on the path you take, okay? So it's an inexact differential. It's not an exact differential like we talked about at the very beginning of class. So, the other thing is it can be completely converted to heat. Right? Well, that has nothing to do with the first law of thermodynamics, but it's important. So we have a system, right? So this is the sign convention for work. If we have a system and if we are doing work on a system, so let's say it's a volume and we're pressure and we're making it smaller, the work is positive. Okay, the value of work is positive. If the system is doing work on the surroundings, so its pressure is higher than the surroundings, so it's expanding, the work is negative. Okay, the sign doesn't mean that it's negative energy or positive energy. It just tells us the direction the energy is moving or the work is moving. All right, so we're defining PV work. What we mean is we've got expansion or compression, and I've shown here this is kind of a piston. We have an external pressure. That's the force we're pushing against, okay? And the gas can expand or contract in the z direction, so it can go dz, one plus or minus, either way. And so the external pressure, since it's force per unit area, we defined it in one of the first videos that we talked about. All right, so we can put force in z versus the unit area of the piston it's pushing on, and then the work is, from a physics definition, force moving versus a force. We can redefine the force in terms of the pressure times the area, right? Because we rearrange this expression, put it in there. Then area times a one dimension, so we're 2 dimension plus 1 dimension is 3 dimension or a volume. So our work is minus the integral of the external pressure dV. Or if we want to take the differential, we get rid of the integral. Okay, so that's the definition of work from physics. All right, so in this case, we're talking about processes where something's happening, okay? And the first set of processes we're going to talk about are irreversible processes. Irreversible are natural processes. And we're going to focus on 3 examples in terms of PV work. So expansion versus a constant pressure. For example, if you're pushing versus atmospheric pressure, or if atmospheric pressure is pushing on you. So we can, here in this case, pressure is constant, so we can pull it out of the integral, and so it's just minus the external pressure times the change in volume. So all we need to do is change the volume. And here I've changed it. I just have the volumes. We can change it to molar volumes, pull the moles out, to make it an intensive property, but we can put moles in to make it extensive again. And then there's this free expansion of gas, which is actually not really doing work, but that's also constant pressure. But in this case, the work is zero because we're not really pushing against anything. So it's just an example of how physics defines work itself. And then the last case of an irreversible is if the pressure external changes as the volume changes. So if we're not pushing any atmospheric pressure, we would likely have a change in that external pressure. If we wanted to know work at that point, we would need to know how that pressure changes as the volume. We would need to have a function, right, to represent how it changes. It's not always easy to do. All right. So the one case where we can get a function is a reversible process. So a reversible process, if you remember, are processes that are basically proceeding along equilibrium. So in that case, that means our external pressure and our gas pressure are the same, right? Because it's at equilibrium, and so we can define them the same. We put it in our expression. Here's our work. This is reversible. Okay, now remember, reversible processes are not natural. They don't happen, but they're useful. So we have our integral. P is a function of V, T, and N. Okay, we've just gone through all of these gases. So let's put in let's just assume that the gas is an ideal gas and plug that in. So P equals RT over V, or nRT over V. We simplify it by using molar volume. So I've gotten rid of, I'm switching back and forth between volume and molar volume, but it's just based on moles. It's pretty simple. So the work reversible is just minus of this integral as we change the volume, RT over VM, dVm. Okay, so at this point, we can't really evaluate the integral unless we know how temperature, because temperature could change, how temperature changes with the volume change, right? I mean, that's something we know happens in terms of gases. So let's do this process isothermally, for example, and then our work reversible, we can pull our temperature and our constant out and evaluate this integral of dV over V, or dVm over Vm, dx over x, which is the natural log, right? So it's minus RT natural log of the V2 over V1. That would be our work for an ideal gas. All right, so we just talked about reversible versus irreversible, and I mentioned it in the previous slide, but it bears repeating. Irreversible process. So every natural process occurs irreversibly. There's no such thing as a natural process that occurs reversibly. Partly because equilibrium means nothing's changing. There's no process in equilibrium. Once you've got the equilibrium, it's done, right? But reversible, at least in when we're talking about reversible heat, reversible work. So reversible work is very important. One, because we could just apply the ideal gas equation to our expression. And two, it actually sets the limits. Okay, so a reversible path is the least amount of work you would need to do to compress a particular system. Okay? So any irreversible path is going to require more work to compress. So that the surroundings have to do more work than the reversible path. And likewise, a reversible path is the most amount of work done by expansion of a system. So if the system is doing work on surroundings, the most work you can get done is through a reversible path. And so you're always going to do less irreversibly. So it's very important. We will use this concept of reversible versus irreversible and this idea that it sets the limits so we know exactly, okay, this is as much as we can do or the least we can do for a particular system. So reversible is very important because one, it's much easier to do unless it's just versus a constant pressure. And it sets the limits of what we're going to learn or what we're going to, how much energy we're going to have to put into a system or get out of a system in terms of work. So next time we will do heat.